again, AP Calculus students. Mr. Record here. We are broadcasting live from Avon High School. It's my Period 5 class. Period 5 class, say hello. You can tell they're excited, right? We got fall break coming up, 2 weeks off, but that doesn't mean that they're going to take 2 weeks off of calculus. I hope not. So we're going to take a look at a related rate problem. Hopefully, if you're watching the video, you may have seen several in the series that I've made here recently about how to solve some of the more traditional related rate questions. This one happens to be example 9 in the notes that we use here. And it's about draining a tank of water that's in a conical sized tank, because most tanks are shaped as cones, apparently. The problem reads, the water is draining from a conical tank with vertex down at the rate of 2 cubic meters per second. The tank is 16 meters high, and its top radius is 4 meters. How fast is the water level falling when the water level is, and we've kind of got two parts to the problem, a part A and a part B. I may just do the part A because by the time we get there, part B is just a matter of plugging in a different number to our final result, and it's not going to change a whole lot of, the complexity of the problem is still going to stay the same. So what we've been discussing with my students here is to begin the problems by drawing a picture, right? Sometimes the pictures are a little bit more helpful than others. We'll see what the verdict is on this when we finish it, but we're going to draw a cone that would be upside down, so it might look something like this. And we know that this cone is going to be full of water, yes? So you can just kind of lightly shade, perhaps, a small amount of water at any kind of random height. It's up to you. So there is our water sloshing around with our little friend maybe in the water. All right, so now we've got our picture drawn. We want to start kind of labeling it, right? We want to kind of get a little bit more information gleaned from this picture. So if we look at the cone and we think about different aspects of the cone, we know that the cones have heights. What is the height of this cone? Well, the problem says the tank is 16 meters high, so that would certainly be a constant of 16, right? The cone is not changing its dimensions. And we have the radius of a cone, which we know to be, in this problem, it says the radius is 4. But then we've got the water. Now, the water is a slightly different story, right? What do you think we want to call the height of the water? Probably h then, right? H is going to be a nice variable to use. We know that the height of the water is changing because it says that water is draining from a conical tank. So the implication here is that this water is sort of kind of spewing out the bottom. All right. So what other kinds of things do we know? Well, we've got this radius of the water, which is again going to vary. You can probably see that the lower the water level is, the smaller that radius is. So we'll give it an appropriate variable name, calling it r. And I think we've done a pretty good job of gathering as much information as we can about the picture. Right. Again, one of the things that I emphasize to my students often when they're solving a related rate question is to provide the given, locate the find, and discover an equation. Now, the given is typically going to be information involving a rate. So when we read or reread the first sentence, water is draining from a conical tank at a rate of 2 cubic meters per second, we can establish the fact that there's no doubt that that is some kind of a rate. But I would like us to identify the correct variable that that rate is associated with. So we have the amount of water changing by 2 cubic meters per second. So what do we think that that is really measuring? The amount of water is really the what of the water, the blank of the water, the volume. Good. And if you're sitting there or you're watching this and you're thinking, well, I would have never thought volume. I mean, that's just kind of coming out of the blue. Check out the label. The labels really reveal what it is that you're trying to discover. Cubic meters is definitely a measure of volume. Cubic meters per second is a rate of change of volume with respect to time. And then there's one other little trick to this. Is the rate of change of the volume increasing by 2? Decreasing by 2, right? Draining sort of connotates decreasing, so we want to use -2. Otherwise, we will assume that the cone is filling up. So there's our given. Our find is usually easy to locate if you just look for the question, beginning with the phrase, how fast is the water level falling? So the water level seems to be indicated by this variable h, so we need a derivative expression for that. And what better one than dh dt? And then, as I said before in this problem, we have two different parts. Part A is going to ask us to figure this dh dt when the height is 12, right? When the water level is 12 meters high. And then part B is going to ask us to do this same investigation, but when the water level is much, much less, closer to the bottom of the cone at 2 meters. Okay? Now for the equation. Well, you got to kind of digest all of the information that you have in the given and the find and the picture and just kind of put it all together. You've got a cone, you've mentioned the word height, but more importantly, you've mentioned the word volume. Hopefully that kind of comes together for you and you can come to the realization that this must be volume of the cone. And the volume formula for the cone is 1/3 pi r squared h, which I know can kind of scare you and think, oh gosh, I'll never remember that. Well, the good news is, in my class, you won't have to. On the AP exam, you won't have to. I can't speak for your teachers out there if you're watching this video, but generally speaking, you know, in a good advanced placement calculus class, a teacher's probably going to provide the same formulas to their students that the AP exam would provide. All right, the last thing that we want to do is see a student struggle with this problem, know all the calculus that's needed to solve it, but have issues because of one formula. So, now is where things get really interesting. Because under normal situations, you probably could take the derivative of this v and do so using the product rule. In fact, in one of my other videos, we maybe looked at solving a problem dealing with, I think, a cylinder or dealing with a, I want to say a rectangle's length and width, where we did take the product rule. But this problem is not quite like that. And the reason is because if we try to take the derivative of this r, or r squared, it's going to produce dr dt's, and of course r is going to hang around. And if you look at all of this information right here, is there anything about r that you see? Nothing. Let alone, you know, dr dt. So that's going to give us sort of a little bit of motivation to realize that r is a bad variable. And we must get rid of bad variables. And if this is the first time that you've seen a cone-related rate question, this might be a surprise to you, how we're going to get rid of this r. But if you're a veteran and you've seen other cone problems, I would imagine that you can predict what's going to happen, because this is typically the case of every cone problem that you come across. So what I'm going to do is go back to my picture, and I am going to use a different color here. I am going to draw in a portion of this cone and then frustrate the students that I have in front of me today mightily by extracting that piece out. Can you guys do that in your notes? Can't do that, can you? But what you can do is you can draw that rectangle. I just want you to realize from where it came. It came from the overall conical tank. It's sort of like a cross section where the top would be how far across? 4. And the total top to bottom distance would be 16. Nice, good. All right, well, big deal, right? What are we going to do with that? Well, then I'm going to do the same thing, but with the water. So if I take that piece and extract it, I know that the distance across the top was denoted by R. It's nice to have that in our original picture. And I know that the vertical distance is denoted by H. And I probably ought to make a big deal out of this, but I want to denote that these two angles are both 90-degree angles. Now we get to see how much we remember from our geometry class that you may have taken 2-3 years ago, I guess. And if we have two triangles that share a common angle up here and also share, a common angle down there, we have two triangles that share this thing called angle, what? Say it, you know it. Similarity. The two triangles are similar. All right? You don't want to get confused and misinterpret this for congruent. Congruent means exactly the same size and shape, right? Similar is more about maybe being the same shape and not necessarily the same size. Basically, with similar triangles, you guys will set up a proportion. And you can set up this proportion a variety of ways. If I start by saying, okay, I'm going to put the 4 in the numerator of my first fraction, you still have 3 different things that you could put underneath that 4 and be correct. But if I commit to, say, 16, in other words, if I say the short side of the big triangle over the long side of the big triangle, now we are absolutely locked in to what we must put on the right side in the correct order. And that would be the short side on top and the long side on bottom. We have to be consistent. Okay? But no matter which ratio, which proportion you set up, after you cross multiply, that's not a 4. Why don't you guys let me write 4? That's an H. All right. R over H. We're going to cross multiply, and we would get 4H equals 16R. You're going to get the same result when you solve for your R. And we could write this as H over 4 if we want to reduce it. So that's the key. Remember R? Remember R, the bad guy, the bad variable? That's what you want to solve for. You are always going to be very concerned about solving for that bad variable because you now have something you can replace it with. All right? So, we move back to our equation. And instead of V equaling 1/3 pi R squared, the R gets replaced by H over 4. Don't forget to still square it. Now, once you're here, don't forget the advice that you had learned probably earlier in your calc class, that if you can spend a little time doing some algebra, it might make the calculus easy. And I can't count how many times I see students still want to use the product rule for this, or just avoiding the product rule completely and taking the derivatives of these two terms separately, which is even worse. Don't do that. Go ahead and square out this H over 4. And continue to simplify. You can see that you've got 3 times 16 in the bottom, so that would be like I think a 48 that you could put underneath the pi. And then H squared times H is H cubed. And now you've got something that really is pretty easy to differentiate. Okay? I'm going to move this up here, and we're going to go ahead and take the derivative of both sides with respect to t. Now, if you're having a hard time understanding this step, taking this derivative with respect to t, you might want to check out some videos over implicit differentiation and kind of bring yourself up to speed. But all I did here is, in differentiating with respect to t, I have to use the chain rule because this variable v is not a t. And then by the time I get to the right side, the 3 comes out in front, 3 over 48 sticks there, along with the pi, lessen the degree of h by 1, and then multiply by the dh dt. All right? And then we're going to go ahead and simplify this 3 over 48 because I believe that is 1/16. But we're going to go ahead and start plugging in all the stuff that we know. That's why all this give and find information is valuable. All right? So the dv dt is -2 from before. And again, I'm going to call this 3/48 pi over 16. The h in part A, so I'm kind of solving part A, like I said. H is going to be 12, so I replace the h with 12. And then the dh dt, well, the dh dt is going to stay as dh dt, right? Because that is what we were trying to find. And then the rest of this is just a little bit of algebraic manipulation, but you still need to be careful. So we'd have -2 equaling 144 pi would be on top, 16 would be on bottom. And I could certainly see this problem being presented to students without the use of a calculator. You got to kind of be a little comfortable, confident here that 144 divided by 16 is a nice integer. I think 16 goes into 144 9 times. That makes that a lot nicer, doesn't it? So then dh dt would just simply be the -2 divided by 9 times pi. And one other thing I want to talk about to my students, and I think this is probably worth mentioning to anybody out there that's watching the video. As a teacher, I absolutely despise the usage of the diagonal fraction bar. If a student were to say this, typically in the context of this question, I would give you the benefit of the doubt. But it is kind of interesting, you know, to look at this and think, is that the same? I mean, is that what this is asking? Is that what this is kind of depicting? But if you were to write it with a horizontal fraction bar, there is no room for misinterpretation. And it's also very important that if you don't use a calculator that has a fraction template built in, and you were going to convert this to a decimal, if you type this into your calculator, this would be all sorts of bad, because it would not know to put that pi in the denominator. You would have to enter it with parentheses to make sure that that happened. All right. Now, if you're using a TI Inspire or a TI 84 with a really new operating system that has the little fraction template that you can call like that up, then you're not going to have a problem. Okay? Hey, one more thing left to do. Give this a label. The rate of change of height is changing by -2 over 9 pi, and it would be measured in, well, it looks like we got meters and we got seconds. Height is certainly going to be measured in meters, not square meters, not cubic meters. And then we look at the answer and we kind of say, hey, should the answer be negative? Sounds right to me. If the water level is falling, then that dH/dt should be negative. Anyway, hope the video helped. I got many more of them for you all to take a look at, and good luck with your calculus. 19.